Let's consider a fourth case where we have two concentric cylinders. The fluid is flowing in between the two cylinders, that is in the cavity. Inner cylinder has a radius of R1, outer cylinder R2. Inner cylinder can rotate with angular velocity omega 1, outer one omega 2. Because of the symmetry, it seems natural for us here to work again with cylinder coordinates, right? Or you can say it's polar coordinates, because we do not consider z direction in our case. You can say that the two cylinders have infinite length, infinite width in the z direction. Okay, so first, with the continuity equation together with another condition, another assumption we make, we can get two simplified conditions in total, right? In before these two simplified conditions, one is called fully developed, the other is called unidirectional, right? Or one directional. Here we can get a similar result. The two conditions we can get is d theta equals to 0. This means the properties of the system doesn't change with angles. Say if I rotate the whole system by an angle, I cannot tell any difference, right? This is d over d theta equals to 0. Another condition is ur equals to 0. That is, I do not have a velocity in the radial direction. This is the radial direction from the center outwards, right? I cannot have a velocity component in this direction. Say if I'm a fluid particle, when I'm flowing, I can only do a circular motion, right? That is, I cannot have the ur, which will make me either go inwards or go outwards, right? I can only stick on my orbit. I cannot digress from it. So this is ur equals to 0. So in a sense, ur equals to 0 means my flow is unidirectional, right? Somewhat called unidirectional, because I can only flow in the theta direction. I cannot flow in other directions. And d over d theta equals to 0 is like fully developed, because my flowing direction is in the theta direction. So d over d theta equals to 0. I can also write out the boundary conditions. There are two in our case, right? The two no-slip conditions. When r equals to r1, then I should have the same velocity as the inner cylinder, which will be u theta equals to r1 omega 1. And the outer cylinder, when I'm at the outer cylinder, near the outer cylinder, then I should have the same velocity as it, omega 2 r2. So now we can write out the NS equations. Remember in the last case, in the third case, our main character was uz, right? Our main focus was uz. So in that case, we only need to write out the NS equation in the z direction. That's because the uz only appears once in all the three NS equations. Well, in Cartesian coordinates, every velocity only appears in its own direction, right? But here, u theta in cylinder coordinates appears twice in all the equations, both in the NS equation in the r direction and in the theta direction. We need to keep that in mind. So theoretically speaking, both the NS equation in the r direction and the theta direction we need to write out, right? So if we write them out and erase all the terms that go to 0, then this is the result we should get. U theta over r squared equals to this thing. This is the equation on the r direction. Or if we do not consider the effect of pressure, then this equation does not give us much information, right? So our main NS equation is still the equation in the theta direction. D squared u theta dr squared plus r 1 over r du theta dr minus u theta over r. This is already the simplified result. So this equation we can solve and get a general solution, which will be u theta equals to c1r plus c2 over r. In turn, we can solve c1 and c2 by plugging in the two boundary conditions. So after some calculations, we can get that c1 equals to r2 squared minus r1 squared over omega 2 r2 squared minus omega 1 r1 squared. c2 equals to r2 squared minus r1 squared, omega 1 minus omega 2 r2 squared, r1 squared. Okay, basically problem solved, right? If we write the final result out, it's just this form: r2 squared minus r1 squared r omega 2 r2 squared minus r omega 1 r1 squared minus this thing. Problem solved. But there's one point I want to demonstrate to you, that is the limit of this case. What do I mean by that? Well, if R1 is very big, that is the radius of this circle is very big, or the circle itself is very big, then the curvature is negligible, right? So this curved thing will just look like a flat thing. Instead of being a cylinder here, it's just like a plate, right? The inner cylinder will just look like a plate. At the same time, if we keep the distance between R1 and R2, the thickness of the cavity to be a somewhat constant value, then R2 will be the same order of magnitude as R1, right? And then both the R1, both the inner cylinder and the outer cylinder will look like a flat plate. So this should remind us of Couette flow, right? Couette flow. If we further let U1 to be 0, only if we let omega 1 to be 0, then only omega 2 are remained, right? So it's like the inner cylinder, or you can say in the limit case, it's just the lower plate, right? The lower plate doesn't move, and only the upper plate can move with a velocity called R2 omega 2, which we'll call it to be U. So we should get the same result as the Couette flow. Do we indeed get the same result as the Couette flow? We can check that, right? So I'll verify that with you. Let's make R2 minus R1 to be of a constant value. That is the distance between the two plates to be a constant value h, right? So R2 minus R1 is equal to h. But at the same time, we let R1 to tend to infinity, and we let omega 1 equals to 0. So here, the coordinates. This, we can say, is a segment of the inner cylinder, right? So maybe the center is here. And this distance is what we call R1. So what we're concerned with now is this distance, right? Not the whole distance. The whole distance we can call it to be lowercase r from the center outwards, right? This distance is r. So this distance is what we are concerned with. That is r minus r1. And this distance we can call it to be x2 because when we study Couette flow, we set the coordinates to be this direction x1 direction, this direction to be x2 direction, right? So this coordinate, this distance should be x2. So here we set r equals to x2 plus r1. Now we can calculate the u. The u theta here just becomes u, right? If we plug all those things in, r2 squared minus r1 squared is just r2 plus r1 times r2 minus r1. r2 minus r1 is just h, and r2 plus r1 is 2r1 plus h, right? 2r1 plus h times h. And this thing we can also plug in. After I do that, I will get the following thing. Well, here, omega 1, I let it to be 0, right? So we don't have this. Minus r1 squared, r2 squared over ru. Remember that r2 omega 2 is just u, right? r2 omega 2 is just u. So this thing is u r2. So now we can divide both sides by u. In turn, we get u over capital U is something like this 2r1 plus h times h, 1 over this. x2 plus r1 squared, r1 plus h minus r1 squared, r1 plus h over x2 plus r1. Which is 2r1 plus h over 1 over this, and x2 plus r1 plus h, x2 squared plus 2x2 r1. Yeah, this is our final result. Well, here, keep in mind that r1 tends to 0, right? H is a finite value. So a finite value is negligible compared with the with an infinite value, right? Here also x2 is a finite value, but r1 is an infinite value. So we can neglect the terms of lower order of magnitude, this thing, and this thing, right? Here we have a finite times infinity, but here is a finite thing squared. So this is still a finite thing. So what we end up with? We end up with this thing, right? To x2 r1 this. So this is just x2 over h. U over capital U is x2 over h. Is this the same result as what we got in the when we study in Couette? Indeed, the same result, right? Which means the result we got here is reasonable.